All right, well, welcome everyone. This is our Boston.NET architecture group, and thank you for joining us. Tonight we have our speaker, Bill Bejeck, who's going to be talking about event streaming in .NET. Really great opportunity to learn about this topic. And so without further ado, I'll turn it over to you, Bill. Thanks.
Thank you. So welcome to, as Robert said, event streaming in .NET. Here we go. Just a quick introduction. I'm on the DevX team at Confluent. Prior to that, I was spent 3 years as an engineer on the Kafka Streams team. Kafka Streams is a native stream processing library for Kafka. And I'm the author of Kafka Streams in Action, and the second edition is due out actually in about a month or so. So what we're going to cover tonight, what is event streaming, what is Apache Kafka, and the task parallel library, and then we're going to take all of those, take both of those components, and then we're going to show how you can build an event streaming application. And I would say at this point that there is a GitHub repo that accompanies this talk that has a working solution, but this is still more of a conceptual thing. It's not something that's running in production, but there is a fully running example in our GitHub repo that's available in the slides. So before we get started, let's define what is event streaming. And I'm going to use the terms event streaming and stream processing interchangeably throughout the presentation. For a formal definition, event processing, it's an approach where the application, its input is events and its output is events. It's really concerned about events. So that leads us to a question: what do we consider an event? And the answer to that is pretty easy. It's that all of your data is events. Everything is an event. If you think about it, life happens to you one kind of event at a time. You don't, things aren't batched up so that at the end of the day, you get all of your phone calls, all your messages and things like that. So if we were to take the example of a bank, there's deposits, there's withdrawals, you have a loan application, investments, you have balance inquiries, a lot of things are going on. Probably most notably would be credit card purchases and fraud detection. You know, I think it's probably happened to all of us. You make a purchase, maybe you travel somewhere or you make a purchase outside of your normal pattern, and you'll quickly get an email or a text that says, hey, you know, is this you? And that's an example of event streaming, because you want to be able to handle those events quickly and respond to them. Now, before we dive into the components of it, we want to talk about some stream processing or event streaming basics, basic areas we would want to have handled. One is time and timestamps, the timestamp of the event, when that happens. Backpressure, the ability to not accept more work, to only handle as much as the application can process at a given time. State management and fault tolerance. These are kind of combined, at least in this presentation. I kind of blur the lines between these two. So it means that, you know, when, you know, an applications crash, but, you know, things happen, especially in distributed environments. So how do you know where you start processing in? And then also, how do you, you don't want to, if one part of your distributed application shuts down, how do you handle it so that you don't have to shut down the whole thing? So the importance of timestamps is an event by itself might not mean much. A lot of times you need some more context or additional events, and combining them together add up to something more important. I always like to use the example of a large sale of stock. That by itself really would mean nothing. But if it happened an hour or, you know, a couple hours before an announcement came out that adversely affected the price of the stock, It doesn't mean that large sale was bad, but it definitely makes you look at it in a little bit of a different light. And so that's where the timestamps of events is keeping track of the timestamps very important. Back pressure is important because certain things you're going to process might be CPU intensive. You might have to reach out to an external service. So you need a way to refuse additional work or only accept as much work as the application can process reasonably. You just don't want to keep piling it up. You want to be able to take in only what you can reasonably expect to complete. And then for state management, if there's a failure, or should I say when there's a failure, when are we going to, where do you resume processing from? How do you resume processing? And then again, in a distributed application environment, if you've got multiple versions of this running, just losing one instance doesn't mean you have to shut everything down. Is there a way to gracefully handle that and continue processing all the data? So now that we've covered the background, we've defined what event streaming is, and we've covered some principles that we want to see, let's get into Apache Kafka. Apache Kafka is a distributed log. And what we mean by the term log, it's not logs where application developers are used to seeing, where you have statements where it's showing sequence of events, what your application is doing. It's more analogous to the log you would have for a database, where it's the log of record. It's the immutable sequence of events. And that's exactly what Apache Kafka is. It's distributed because you usually deploy brokers in a cluster. And so this log is replicated and split up across all the brokers in a cluster. As records come in, they're always appended to the end. So it gives you this implied sequence of time, because since the records are always appended to the end, you have a natural time ordering of your events. Now, as they're appended to the log, they're given a number called an offset, which represents the logical position of this record in the log. Now, it's not, of course, this is going to grow over time, so these are broken up into segments. And to further differentiate the log, Kafka has a concept of a topic, which is a name you would give to maybe say a certain category of events. And so, like if we use our banking example, you might have, say, a withdrawal or a financial transaction topic that would record withdrawals and deposits in that log. Now, the records in Kafka there's a record and it has a header which contains just generic information. And then you have a payload with the key and the value. Well, I'll talk about in the next slide the importance of a key. It's not required, but that's the basic. It's a pretty simple structure. Now, I had mentioned that Kafka breaks up the event log into different categories called topics, and the topics are named by you create the topics and add those to just create those in your broker cluster. But topics are further broken down into something called partition. Partition is the unit of parallelism in Kafka, and it also serves to break up the load of a topic across all brokers. A particular broker in the cluster will be identified as the lead for a topic partition, and all requests either for appending to that topic, adding to that topic, or consuming from that topic go through the lead broker. And again, with partitions, you get a unit of parallelism. So usually more partitions mean higher throughput. Now, the way records are determined to go onto a partition is you take the key, you hash the key, and you modulo that number by the number of partitions, and that determines where the record goes. If there aren't any keys because they're not required, then an attempt is made to, over time, to evenly distribute all the records across partitions. Now, I mentioned Kafka brokers are deployed in the cluster, and here we see three. Three is the kind of the nominal broker size of those. Certainly they can, I mean, cluster size, but certainly they can grow much larger. And I'd mentioned that a broker is considered a lead for a given topic partition. So the way this works is you would have each broker would be responsible for a certain number of topic partitions, but the ones that aren't responsible for it are considered follower brokers. So here, the one in front there, the broker there is responsible for that topic partition on the right, but the other two behind it are considered followers, and they're going to fetch records from that lead broker so that over time, so that your data is persistent. Replication factor of 3, your data would be persisted across all three brokers. Now, to keep track of this, to keep track of topic partitions and which brokers are leaders for which topic partitions, Kafka uses metadata. Currently, and historically, Zookeeper was used to keep track of that metadata. But a couple years ago, KIP 500 came out, which was to replace Zookeeper with Kafka's own metadata service, and now it's called KRaft, which uses Kafka brokers itself to keep track of the metadata. The most recent release of 3.4 saw KRaft as production ready, although Zookeeper is still available. It's still the default. And future release coming out pretty soon, Zookeeper will not be an option and will be gone. And it'll just be using a KRaft to keep track of the metadata. Now, Kafka's are a broker. I mentioned brokers, and they are the storage layer, if you will, for incoming records. So you have to interact with Kafka via clients. Kafka is written in Scala, but that doesn't imply that you have to use a JVM language to work with it, because Kafka just defines a protocol. And if a client adheres to that protocol, the broker really is client agnostic. It doesn't really care. It's going to accept produce requests or consume requests from a client. So tonight, specifically, we'll talk about the .NET clients. So it's really language agnostic. So you have a producer client that's going to send batches of records to the Kafka broker. Now, the producer will determine the partition that a record goes to using the mechanism of hashing the key. Those records are sent to a partition, topic partitions. But then you have consumers that can consume from topic partitions. And the way it works in Kafka is you can have up to, here we've got a topic with 2 partitions, which is kind of low. Typically you can have, it's not uncommon to get partitions in the 10s or 100s. You can have up to a consumer per partition that's consuming these records. Consumers with the same group ID are logically considered like one large consumer group, but by being able to specify more than one, you can increase throughput by having a dedicated consumer per partition. Now, to go back to some of the principles of stream processing I was talking about, when you give a record to the Kafka producer, messages are sent in a batch. I'm showing one here, but they're sent in a batch, and that's determined by the producer when it feels it's time to send a batch. The producer was going to create a timestamp and add that to the record. So assuming that your producer is very close to accepting the events that are happening in your application, this satisfies our need for keeping track of this timestamp. This is the event timestamp. Now, you could add a timestamp to your record itself, the payload, because you give Kafka a key and a value. The value record you give is going to be serialized into bytes. Kafka brokers only accept requests in bytes and then fulfill consume requests. They're also passing out bytes. So it really has no idea of what you're storing. It just takes the records, appends them to the log at the given topic partition. But at any rate, this timestamp effectively can be used to record the event time of when whatever happened that you're passing into Kafka. Now, the consumers, you're going to send a consume request, and then you're going to get records, and then you process them. And so the question is, how do you know, in case of a failure or a shutdown, how would you know where you are? Where would you start? Where would you start over? Consumers leverage the offset that is assigned to a record that comes in, and consumers' clients keep track of their own partition. They persist them in a Kafka topic, what's considered an internal Kafka topic, but the broker doesn't keep track of producers or consumers. So consumer clients are responsible for recording their own position. So what they do is you process a batch of records, and then you're going to commit you're going to commit the last offset you processed plus one. And so that's where you're going to fetch your next batch. So for the example here, we're saying the committed position is 4. That means this particular consumer processed record 0 through 3, and then it committed offset 4, which means that's where I want to start. Now there's a difference between the committed position, which is where it left off last time, where it's going to fetch its next batch. And now its current position is 8, meaning it committed and it fetched the next batch that's currently working on. So its current position is 8. So when it commits again, it's going to commit at offset 9. Now, this is important because this gives us state management and failure handling. Because in case of an error, you've consumed records, you're processing them, but an error happens or you shut down. Well, your consumer is going to go back and pick up again at offset 4. So this gives you at least once processing, and this is how we fulfill in stream processing guidelines of handling state. Each consumer is going to know where it left off. And further failure handling, error handling, is I mentioned you can have multiple consumers, each assigned a given number of topic partitions. If a consumer, there's a couple ways a consumer can get kicked out of the group. There's a couple of timeouts that are set. But if a consumer is determined unresponsive, it is kicked out of the group, and something called a rebalance occurs. And what that is, a rebalance is just really taking the topic partitions that were assigned to the previously to the non-responsive member of the group. Those topic partition assignments are taken away and reassigned to the other active members of the group. Here, it's pretty simple to keep track of because we only had 2 partitions. So we lost one member of the group, so that one partition is assigned to the other active member. It's going to make every attempt to evenly assign topic partitions to the active members of the group. But if you have an odd number of partitions, then you're not going to be able to do that. Now, so that takes care of, that's how clients interact with the Kafka brokers. And, we've demonstrated handling of timestamps and fault tolerance and state management. There's one more thing I want to cover before we move on. As I mentioned, Apache Kafka is written in Scala. It's the default clients that come with the Apache Kafka distribution are written in Java. For non-Java clients, there's a librd Kafka project, which is the C++ implementation of the Kafka protocol. And there's additional clients are built on top of that, namely Python and C#, which is most relevant for our discussion tonight. These are built on top of librd Kafka. Now, I mentioned that partitioning done by the producer uses a hash, hashes the key to determine the topic, determine the partition the key needs to go to. The default partition used by librd Kafka, so by extension, the C# or .NET clients, is called consistent random. Under the covers, that's using CRC32 as the hashing algorithm, which is fine. And then if you don't have a key, they're randomly distributed to a topic, a a random partition. So over time, it should evenly distribute those non-keyed records. But the interesting thing is the Java clients, their default partitioner, and there's only a default partitioner in Java, uses the Murmur2 hash. And so in today's polyglot programming world, which is natural, you can have people within the same organization using different languages. You could have producer clients, non-Java producer clients, and Java producer clients, and they're not going to be using the same partitioning scheme. So you really want to use the same partitioning scheme across all clients. So fortunately, libRD Kafka does provide, in C# by extension, provide multiple hashing algorithm, multiple partitioning approach. So if you are using Kafka in the C# client, a good practice would be to set the partitioner murmur to random, and that's going to give you the identical behavior of the Java clients, producer clients. So we've covered what event streaming is and Apache Kafka and the clients, how that all works. But we need something to fill in. You're going to consume records and you can produce records back to Kafka. And another topic, you've done some sort of transformation, but we need to fill in the middle. What do you do after you consume a record and you've done some kind of processing? And this is where the task parallel library comes in. The task parallel library is from Microsoft. It's public API that's aims to make writing concurrent programs easier, simplifying the process. Writing concurrent programs is difficult. And so TPL aims to make this process much easier. Now, we're going to talk about tonight, what I'm going to be speaking about is a specific subset of TPL is a very large library. I'm talking about one specific part of TPL called Dataflow. Dataflow gives you blocks where you can pass messages in between blocks. And very importantly for our purposes, they process data when they're available, when it becomes available. Now, what you do typically is you're going to take these blocks and chain them together to form a processing application. You have a source that's going to get input from somewhere, and then you chain blocks that can perform different functions, ultimately ending in a sync block that you could use to write the final results out to an external source. There's three general categories of these blocks. You have a source block that could be the source for the whole application or source for another block within the chain. The target block is one that accepts records, possibly the terminal end of the application. And then you have a propagator block, which acts as both. It can be target by accepting records from a previous block, and source where it provides records for another block in the chain. Now, these concretely, you've got a buffer block, which you've got the generics of type T. This is the most basic building block in the Dataflow library. You have a broadcast block, which can write to multiple blocks in an application. Transform block, which you would use to take an input of one type and output another type. A joining block for combining results. And then you have an action block, which is just like a generic action you want to perform on a record, but you're not going to change its type. So given these, and this is just a subset, there's many more. This is just kind of the most common ones you could say. So taking these together, you can build up a complex topology of processing things, all from a source. And how the blocks specifically work is you're essentially just going to write a function and provide that to the block, and it's going to apply that for each record that it accepts from a source. Now, Dataflow provides a couple of unique things that make it well suited to building a streaming application. The first of which is an input buffer. I mentioned earlier, for our requirements of stream processing, you need the ability to apply back pressure. So with an input buffer in a block, you can define how much you want to buffer, how many records you want to buffer. And then once the buffer reaches that size, it will reject any additional input. So this allows you to control how much input you can take. So you can set, a reasonable amount of data that your application can process. The next thing about Dataflow that's unique is you can specify a concurrency level for the block. And what's particularly interesting about specifying the concurrency level, here we're going to say it's 4. So we're going to get 4 threads that are going to work on this particular transform. Typically with concurrent programming, you can't be guaranteed the order of results. But with Dataflow, when you specify a concurrency level greater than 1, it guarantees you that your output order is going to match the input order. Now, you're not guaranteed the order of how things complete within the block, but the output of when this block starts emitting results, it's going to mirror, it's going to exactly match the input order that came in. And I was a little skeptical of this, and I'll talk about this later on. I ran my own test to confirm this. And this is also important for us in terms of, since we're using Kafka, I had mentioned that records, when you send a produce request, when you give records to Kafka, the broker, they're appended in order, they're appended at the end of the log. So you're getting those in order. So the consumer consumes these records in the same order. So you're getting them in time order. The order is guaranteed within a partition. So the fact that you can maintain order through your processing, through your application, even with concurrency, is very important. So this allows us to apply concurrency, but maintain the order of our records. And how this is the actual code that you would write for a given block. This is a serialized function. And it's this simple. You just write the code that you want the block to perform. So this is essentially how it's very straightforward. You get your function, you define block options, which you set your bounded capacity as your buffer size and your max degree of parallelism. The default is 1, and maintaining the order is also the default. So you take these two, you take your function, your block options, and then you just instantiate your Dataflow block and pass these 2 in. So you're getting a lot. So all the heavy lifting is being done for you. And we'll see how you connect these later on, but basically connecting the blocks, the parallelism, and the buffering, all that's handled for you. So you're really focusing on your business logic. So next, we need to take these raw components and, let's put these to use in building an application. At this point, you can probably see where I was going. A Kafka consumer is a great candidate to embed in a source block to feed a Dataflow block, a Dataflow application. And again, this is a simple linear thing. It could be much more complex I'm showing here. And then the Kafka producer works greatly in a sync block or a target block that's going to get the final result of an entire processing chain and write that result back out to Kafka in a topic for some other downstream consumer to look at a final result. So most of Dataflow gives you predefined blocks, and you just instantiate them. But they do give you options to kind of create your own. So that's what I've done here, is an interface, the source block interface. And that's just a wrap around a consumer, a .NET consumer, and a buffer block. And what we're going to use this internal message buffer for is, as we implement the interfaces on the source block interface, we're just going to delegate to our message buffer. And so that just makes, so we're even though we're implementing an interface, we're not really writing, again, we're deferring all the details to the TPL, Dataflow. And for the producer, we do the same thing. We implement a target block, again, wrapping a message buffer and the producer for writing the results back out to Kafka. And finally, well, not finally, but this is, so you've created your different blocks, and this is how you tie it all together. You have a source, and you're going to link to your deserialize. And you take your deserialize, and you map that, you link that to another block. And this builds up your application. So it really is a nice way to package something up. So now we have a fairly complex application, but it's concise to put together. Now there's a couple of things we need to deal with, bookkeeping things we need to deal with. One is, I'd mentioned committing. Typically, the workflow with a Kafka consumer is you're going to consume some records. You do this in a loop. You're going to consume some records, process them, and then you return to the top of the loop. You commit the offsets of what you just processed, and then you're going to fetch another batch of records. You can manually commit, but there's also a notion of auto committing. And as long as you've fully processed everything, when you get back to the top of the loop, that's a great way to go. You commit your records and you fetch another batch. But we're going to do things a little differently and take advantage of the parallelism that we get with Dataflow. We're going to consume records, but we're going to hand them over immediately to the processing pipeline. We're not going to wait for them to be fully processed. We're not going to wait around for that. So that leaves us with a bit of a problem potentially, because we could, since we're not waiting to acknowledge that everything's been successfully processed, we could commit, and our commit could outrun our current processed position, our current processed records. And what I mean by that is, imagine a scenario you processed records 0 and 1, offset 0 and 1. You commit, so you're going to pick up your next batch, you start at 2. You grab records 2 through 6 in your next batch, you start processing. 2 and 3 are successfully processed. You commit, which is going to be offset number 7. You always commit 1 plus the last successfully processed record, because then that's where your next batch starts. But we don't know if 4, 5, and 6 have processed successfully yet. So we could end up potentially losing data because we're not going to, if there's a failure, we shut down. If we commit early, we're going to pick up processing at offset 7, missing 4, 5, and 6. So the way we handle that, we take advantage of the fact that the .NET client does something for us that we actually don't even get in the Java client. When we consume a record, we take the key and the value, but we're going to preserve the original offset. We're also the timestamp and the source topic. But right now, I just really want to focus on the offset. We're going to preserve that through the entire processing pipeline. So no matter what sort of transformations you do, whatever happens, you're always creating a new record. You're passing along that offset. And what that does for us is when you get to the sync block at the end, you have your Kafka producer sends the record, produces to the broker. It gets back an acknowledgement. Yes, I've successfully stored this record. Only at that point will we're not even going to commit. We're going to take that offset and hand that back to the consumer. So what we're doing is we're still going to use the auto commit feature that when it goes back to the top of the processing loop, it may call commit, but it's only going to commit the offsets that we've explicitly handed to the consumer. So we know when a commit has been called, it's only something that's been successfully processed. And how this looks in code is this is inside our sync block. The internal message buffer receives a message from previous block in the chain, and it creates, we've got this delivery handle method, which is a callback. And down at the bottom there, that last line in the screenshot, we call produce. And this delivery handle is executed at the end of the produce request. And if it was successful with no error, we pass the record to something called the commit observer, which is just an abstraction around our consumer. And so we, in the onNext method, we take our process record, we extract the source offset, and we hand it to the consumer. We say store offset, so that the next time it calls commit, it's going to include this offset in the offsets to commit. So this guarantees us that we're only going to, so we're not going to outrun our current position. So when we commit, we know we've successfully processed a record. And if there's a shutdown for any reason, we're going to resume processing. Even if something was within the pipeline, we're going to resume processing at our last committed offset, which is going to give us, again, at least once processing. Now, the other thing we have to account for that's tricky with stream processing is, I'd mentioned back pressure. So we're just handing these over to the processing pipeline. But what if things slow down and we don't want to go and fetch another batch of records from the broker? Kafka consumers themselves don't necessarily need back pressure because you're using them in a loop. So they're only going to pull records when they need them. So in this case, we need to basically have a mechanism to tell the consumer to wait before it fetches another batch. And this is a code snippet from inside the source block. In Dataflow, when you post a message or post something into a block, it returns a Boolean whether it was accepted or not by the next block in the chain. In this case, while a record is rejected, we're just going to wait until there's space in the buffer, and then we'll resume consuming again. That's just a repeat of the code from the in the commit observer when we extract the offset. And then to take advantage of this, we still enable auto commit, which means when it returns to the top of the processing loop, it may commit. But we tell it to not store the offsets. It doesn't keep track of the offsets that it consumed. We want to tell the consumer what to explicitly commit. And then getting back to the concurrency factor, I wanted to see this work in action. I also wanted to test the in-order processing. So to do this, produced 1 million records to a topic, used a parallelization of 1, and then I also put a block in there that had a sleep time of 1 to 4 seconds randomly. Produce 1 million records, shut down, record the time it took to process. And as you would expect, that worked really well. So just by restarting that process and specifying concurrency factor of 4, we get the expected speed up. I ran that just on my laptop, but we get the expected speed up of, we would think by adding 4 threads, we would get a speed up of 400%, and we got that here. But there was still, I wanted to see in order. I was still a little skeptical of the in order. So I repurposed my concurrency test and just produced 1 million integers to a Kafka topic. And then I created a blocking, again, using used a random sleep of 1 to 4 seconds. And it was just really just an echo application. I would consume, it would just consume and then write back out. But again, I had a block in the middle that was sleeping from anywhere from 1 to 4 seconds. So basically at the end, we have another topic I've written to with integers in the same order, 0 to 999,000. So that was with a concurrency level 1. I consume that topic again, but set concurrency level 4 and produce that to a different Kafka topic. Then I consume both of those results and store them in an array in memory. And I compared both of them and I confirmed that they were both in identical order. So the concurrency level matching the output order, matching the input order works as advertised. So in summary, Kafka is a standard for event streaming. You can use it think of it as a central nervous system for handling events in an organization. The .NET clients give you the ability to produce and consume. Again, Kafka is written in Scala, but it doesn't matter because the .NET clients speak the Kafka protocol. So it really doesn't matter that it's written in a language. Dataflow blocks kind of fill in the space in the middle between your consumer and producer clients. And you can combine them, both the .NET clients and the blocks, to build an event streaming application. And I also, and here's resources. I'll give Robert the slides when we're done. So this has resources for some of the things I was talking about today, the GitHub process, the GitHub repo, the .NET clients, Dataflow, and also Kafka Streams, I mentioned earlier in the talk, is the native stream processing library for Kafka. That is written in Java. A colleague at mine at Confluent has ported that to .NET. So this is something else. If you want to get into stream processing, I would give this consideration. And finally, Confluent Cloud is hosted service for Kafka. So you would end up really, the management of the brokers and everything is handled for you. You don't have to use Confluent Cloud, but this just alleviates having to manage a distributed application. So this would just, you get your endpoint, point your clients to it, and you're off with stream processing. And that's what I have for you tonight. Thanks for your time.
Yeah, thank you, Bill. Does anybody have any questions? I have a couple. So I know Kafka is one option. I think there's Pulsar and RabbitMQ and maybe a few others. But in terms of choosing Kafka, is there what are some of the criteria for that one versus maybe something else? Or yeah, if you could maybe talk about that a little bit.
Well, the difference between, say, Kafka and like an MQ series, or I don't know if JMS is also another one, but that's just in the Java world. Messages are, for a lot of these messaging queues, messages are ephemeral. It's produced, it's consumed, and it's gone. Kafka persists them, so it's always there. You always have this transactional history available to you. So if you need to rerun things, you can go back in history. So it's important to be able to process events as they happen, but a lot of times you need to go back in time and look at something. So Kafka gives you that, it's persisted. Now it's how long it's persisted is configurable. The default is a week, but you can, the New York Times uses Kafka, and they've used that. They've got storage external, and they persist everything that they've ever written in Kafka. For something like Pulsar is probably, it also offers persistent storage. It's a little more complex. It's got more moving parts. There's some, I'm not as well versed in it as I should be, but it's I guess it doesn't offer all of the functionality that Kafka does.
Okay. I appreciate it.
Sure.
And then let's see. What's I know you've got a book, so we'll definitely promote that as well. But in terms of just ramp up time, I mean, this is a great presentation for introduction for folks if this is the first time. But also, I remember years ago using the task library, learning that with a few other things and so forth. And it takes a little bit of time. But what are your thoughts on, somebody just getting started and ramping up, typically to take some time or allocate some time to learn and increase their skills on this?
Yeah. I would say it kind of depends. If you have a background in concurrent, if you've done multi-threaded programming in the past, it'll really help. So I guess in that respect, TPL and Dataflow in particular is great in one respect, but difficult in another because it does abstract a lot of the details away from you. So if you're not really familiar with concurrent programming, I guess you could end up shooting yourself in the foot. But in my opinion, it's well thought out. Picking it up, and I'm not I probably should have said this at the beginning of the presentation. My background is mostly Java. I'm new to C# in the .NET world. And I found TPL pretty easy to get into. The documentation is good. Depending on what you want to do, I would say, let's put it this way, for the simple cases, the more straightforward things, it's great. If you've got more complex things you want to dive into some of the nittier details, I think it would take time. But at least with Dataflow overall, I don't think your ramp up time would be that significant, because the biggest things you have to determine are your buffer size, concurrency level, and then connecting the blocks. But so many of those details are handled for you. I think error handling would be the tricky part. You would want to, I don't know if you'd want to like let one of your buffers fill up completely if there was an error. So you'd have to determine. That was one thing I didn't do in this case, because I said it's more of a conceptual thing. But you would want to see, if an error occurs, depending on the type, you'd probably want to shut down the flow of records into the application. So that might take a little time to get those settings exactly right, because each block they don't really have knowledge of each other. You connect them, it just knows that, hey, I'm going to send something to the next thing in the chain. So error handling, I think, becomes more important. So that might take a little time to get that worked out.
Okay. Yeah, great advice. All right. Anyone else? All right. Well, Bill, thank you again.